Today we'll be talking about the enthalpy from heat of formation. So just a quick review. So far, we have calculated the delta H, or the enthalpy of reaction, by multiple different ways. We've looked at Hess's law, right? And this was the sum, where we did a sum of the equations. We've looked at temperature change using Q equals mCp delta T. And then we've also looked at delta H from a phase change, right? And that was the enthalpy of fusion for when we're going from a solid to a liquid, and the enthalpy of vaporization from when we're going from a liquid to a gas. Well, today we are going to expand on that, and we're going to take a look at the delta H of formation. Okay, so let's dive in to heats of formation. Alrighty, so let's change colors because black and white is just too bland. Alrighty, so the heat of formation equals the energy when compounds are formed from elements in standard state. Okay, so this is only work when we're looking for the energy forming a compound from elements. Okay, just a side note, this is usually negative because it's a lower energy state. Right? Molecules typically have less required energy to maintain it than a bunch of individual atoms zooming around, right? Alrighty, so let's take a look on how we would go about doing the heat of formation. So heat of formation is delta HF. Don't get confused with fusion. Fusion, we put FUS. This is the oops, what am I doing? I'm trying to spell enthalpy and not thinking. Enthalpy of formation or heat of formation. We use them interchangeably, okay? Alrighty, so if we wanted to do, let's do a quick example. Let's do the heat of formation of CO2 gas. So what you need to do is CO2 gas is what's being formed. We need to break that down into the elements in their standard state. Okay, standard state will be, most of the time it's going to be, so for carbon it's going to be a solid. And O2, remember that's one of our diatoms? So we're just going to break it up into O2, and that's going to be a gas. All right, you can look up the heat of formation for CO2. And it will be, or I guess this equation, we'll just keep it delta H, but it would be the, looking up the heat of formation for CO2, it would be negative 393.509 kilojoules per mole. Note this is in per mole, kind of like when we were working with fusion and vaporization enthalpies, right? Alrighty, so let's practice looking at and writing these equations. All right, so write the delta H formation equations. Okay, so for this first one, we're going to write it for BaCl2. Well, for this, Ba is going to be a solid in its standard state. Chlorine is one of our diatoms. Let's actually look back at, remind ourselves what the diatoms are. If we look at the periodic table, remember if I were to group these out, we do a nice 7 here. These are going to be our diatoms. Okay, most of these, especially the ones in this upper area, these are going to be mostly gases. Diatom, remember that means that they're going to be 2 of them. So we have N2, O2, F2. These are all gases. These are going to be their standard state. Anytime you're working with nitrogen, oxygen, fluorine, chlorine, bromine, iodine. All right, so let's go back. Most of the other things will just be solids. So barium's no exception to that. It is a solid. Chlorine, it's one of our diatoms, so it's going to be Cl2, and it'll be a gas. We'll form our BaCl2. So you see how I'm taking the elements and I'm breaking them down to form what they are. Now, if you look that up, the enthalpy of formation is going to be negative 858.6 kilojoules per mole. Let's take a look at another one. Let's do glucose, the wonderful sugar molecule. Okay, to make up glucose, I need 6 carbons, right? I've got 6 of them there as a solid, plus, right, hydrogen is also one of our diatoms. Yes, it's not in that 7, but hydrogen is also one that acts like this. Remember, hydrogen kind of, its placement on the periodic table doesn't always follow the same trends as everything around it. It does form a diatom. Okay, so it's going to be H2 gas, but to have 12 of them, I need to have 6 here. Okay, oxygen, that's one of my diatoms, so it'll be O2 gas, and I will need 3 of those to make the 6. So this will form my glucose. All right, and it has a delta H of formation. You can, again, you look this up, is 1,271 kilojoules per mole. All right, let's just do one more. So that way you're starting to get the feel for it, okay? So for this last one, it's going to do, let's do CH3OH. Okay. So looking at this, okay, we've got carbon. We've already come up with carbon's going to be solid, right? We've got H2 gas. So it's one of our diatoms. If you look at this, I've got 3 here, but I've got 1 here, so I need 2 of the H2 to get 4 total. And then I've got O2 gas. Now, in only to have 1 of them, it'll be a half. For these, it is okay to have fractions, because the idea here is that you want to have exactly, not multiples, of the molecule you're working with. Because when you look it up, the heat of formation would be for this equation for only 1 of this product. So you'd have to have half O2, and that is okay for this. Alrighty, so if this is a liquid, the heat of formation is 238.4 kilojoules per mole. Now, if this is a gas, it actually has a different heat of formation, because that will change things. Just like we noticed with, like, vaporization and fusion, the enthalpy is dependent on the phase, right? So if it's a gas, it's actually 201.0 kilojoules per mole. All right, so now we've figured out how to break these up and how to look things up, right? All right, so let's do an example for a bigger equation. So if I've got 6 CO2 gas and 6 H2O liquid goes to C6H12 O6 solid plus 6 O2 gas. All right, hopefully you recognize this. This is the respiration system for plants. Plants take in CO2 and water, producing sugar for themselves, and then releasing O2 into the air, which is why we love plants. They give us plenty of oxygen. They take our CO2 that we breathe out and form it into oxygen. All right, the chemical formula for this is great, but let's look at the heat of formation for this, okay? So you would look up the delta HF for each of them. So I'm just gonna put it here. For CO2, it's negative 393.509 kilojoules per mole. We're gonna run out of room. For H2O, it is negative 285.8 kilojoules per mole. Alrighty, for glucose, it's negative 1,271 kilojoules per mole. And oxygen is already in standard state. If it's already an element, remember, for heat of formation, we're looking for compounds. This is an element, so it's just going to be 0 because it doesn't, we don't take it into account, okay? All right, because it doesn't require anything to form. It is already in its elemental state. No formation needed. Okay, so we're going to treat this like we did Hess's law. So we need to break up each of these. So let's take a look at the CO2. That's going to be solid carbon plus our O2 gas goes to CO2. Okay, and we said the delta H for this is negative 393.509 kilojoules per mole. Okay, looking at the next one, I'm going to give myself some room. All right, we've got H2 gas plus O2 gas, and we're going to need only a half of the O2 to make H2O liquid. All right, and we said that the enthalpy for this one is negative 285.8 kilojoules per mole. Okay, now we've got the glucose. Remember, we broke this one down already. So it was 6 carbons plus 6 H2 gases plus 3 O2 gases gives me my glucose as a solid. And this has an enthalpy of negative 1271 kilojoules per mole. So for formation, you will be given those numbers up top, but you would have to write these equations. Now let's go about it like you would do for Hess's law. Okay, so we want the CO2 on the other side, and we need it to have 6 of them. So we're going to multiply the whole thing by 6, and then we're going to switch it around so that way it's on the other side. Apparently it will not let me write another parenthesis over there, so just pretend there's a parenthesis on that. All right, we need to switch around to put it onto the reactant side. So we now have 6 CO2 goes to, I don't know why I wrote it so far over, but oh well, 6 carbons, oops, as a solid, and 6 O2s as a gas. Okay, when you flip it, remember that changes the sign. So let me multiply this by 6 really quickly. 6 times 393.50. Whoops. All right, so this now is no longer going to be negative because we flopped it all. It'll be 2,361.054. Not going to bother with rounding at the moment. Okay, now it's positive. Remember, let's cross out the previous one so that way we don't get it confused when we go to add things up. All right, water we also want on the other side, and we also want 6 of them, so we're going to do something similar, right? We're going to flop it around and we're going to multiply it by 6. So we now have 6 H2O goes to 6H2 gas. And 1/2 times 6 is 3 O2 gas. And it'll give me an enthalpy of 1,714.8 kilojoules per mole. And remember, we made it positive. It used to be negative. We made it positive because it's been flipped around. Okay, cross that one out so we don't get confused when we go to add things up. All right, I have the correct number of glucose molecules. Yay! Okay. And then we do need to add in an equation for the oxygen, right? Well, we don't have to, but for posterity, let's do. It would be 4O2 goes to, as a gas, 4O2. And that enthalpy is 0. So it doesn't really count in, right? All right. Let's go through and let's add things up and see what happens. Okay, so I don't know why I made it 4. In my original equation, I needed 6, so let's make it 6. Doesn't really matter. All right, let's erase that and make that prettier. Wow, really erased. Okay, forgot that I have it on really big. So we're not gonna bother too much with making it too pretty. Call it good. All right, let's go through and figure out what cancels out. What do we have that's on the same on both sides? Oh, I've got 6 solid carbons. Okay, cancel those out. I have 6 H2s. And I've got 3 O2s. I've got the 6 and the 6 O2s, which is why it didn't really matter if we had it in there or not. Now, let's see what we have left. We have 6 CO2 gas plus 6 H2O liquid goes to our 6 O2 gas plus our glucose. Let's take a quick peek back. Is this the same thing? Heck yeah. We might have had things in a different order, but it really doesn't matter, okay? Now let's add up the enthalpies. Alrighty, so we have, give me 1 sec to add these. 1, 2, 7. Alrighty, so this gives me an enthalpy of 2,800, and we're going to round it to 5 just for simplicity. All right, that is my enthalpy. All right, so you can do it this way where you break it down into its elements and then do Hess's law. But is there an easier way? Yes, there sure is. So let's take a look at the easier way. All right, easier way. Takes a lot less steps. All right, it's going to be you write the heat of formation or the enthalpy of formation under the species. Then your delta H is going to be equal to your delta H of formation of the products minus your delta H of formation of the reactants. Okay, so let's take a look at an example of that. Okay, so using the same thing that we just did, we had 6 CO2 gas plus 6 H2O liquid leads us to our glucose, that's a solid, and oxygen. Okay, if you write the heat of formation under each of these, right, this is something that would have to be given to you. Oops. right? So we got negative 393.509. We had the negative 285.5, negative 1271. Remember, you're not going to find oxygen. It's 0 because it's already in its standard state, is already the element. Okay, so now our delta H of formation is going to be equal to, we add up our products, you are going to have to multiply it by the coefficients. Okay, so first, let's add up our products. That's going to be negative, come on. All right, our products are negative 1,271. I only have one of them, so I don't need to multiply. Plus 0, doesn't matter. Don't need to write that. Minus, all right, minus our reactants. Let's take a look at our reactants. We've got 6 CO2, so it'll be 6 times our negative 393.509 plus 6 times our negative 285.5 because I've got 6 H2Os equals, you add it all up, you'll end up with 2,805 kilojoules per mole. So much easier. All right, so the key is you are going to want to memorize this reaction. Oops. Oh, sorry. Memorize. Okay, it's going to be products minus reactants. You're going to sum up all of your products, heat of formation, and these will be given to you, or you can look them up, right? Make sure that when you're doing it, if you have any coefficients, you multiply your heat of formation by that coefficient. And that's all you have to do.